What'd she do?
We're going to review thermochemistry a little bit today, and this is from your review packet. A couple things I want to go over just to make sure you're remembering a few things, and then we'll take a look at an AP style question. First of all, even in honors, you learned about Q is equal to MC delta T. When you have a change in temperature, you'll use this formula. I do want to remind you, in regard to the mass, this can pose a problem, so let's make sure we're clear on it. So if you have Q is equal to MC delta T, if you have something like a burning potato chip or the ethanol that was burning in a previous practice question we did, that's where you're just looking at the mass of water, because heat will be transferred from the burning potato chip or from the alcohol burner to the water. So you're not going to start adding things together for mass. However, if you dissolve, for example, 5 grams of magnesium sulfate, and this was from the Thermo lab we did this year with the hand warmer design, and you add it to 100 grams of water, then the mass is the sum of the two. So be careful there. If a substance dissolves in another, if you dissolve a solute in a solvent, then you're going to be looking for the Q of solution, so you'll add the two together. If, on the other hand, you've got heat transfer from, let's say, a burning potato chip or a burning piece of food to water, that's when you're just going to have the mass of the water or whatever you're transferring heat to. So be careful there. If you have a change in temperature, you can use this. Now, with a phase change, delta T is equal to 0. So that's where you're going to need either Q is equal to the mass times the delta H of fusion. You'll use this for freezing or melting.
Melting will make it negative though, right?
That's backward. Freezing negative, melting positive. Melting is endothermic. Remember, men. They'll usually melt your hearts. Melting is endothermic.
Demonstrates God. Gotcha.
I see a proposal coming on. Delta H of vape here. So that's going to be for vaporizing, boiling, and condensing, with these two being positive and condensing being negative. Yes, yes? It's looking familiar? So for a phase change, you can't use this formula. Instead, you'll use this. Now in AP, we also put these formulas together a little bit. And that's because, let's say, for example, that you melt something and then it hits its melting point and then you warm it. Then you're going to need a combination of this plus this. So be careful there. Specific heats you don't need to memorize, they'll be provided to you.
So will the delta H fusion and stuff like that?
Yeah, those will all be given. The other thing I'll mention here, I think it's below, but it seems like it's on a good track. Delta H is equal to the Q over the N. And for example, if you're talking about, again, dissolving the mag sulfate in water, you'll get the Q where you have the sum of the two here, but the N will be for moles of magnesium sulfate only. So it'll be the moles of whatever you dissolved. first law of Thermo, so this is strictly at the AP level. The change in internal energy is equal to the heat plus the work. When heat is absorbed, we know Q is positive. When work is done on a system, this is like going to get a massage. Somebody does work on you, so your back feels good. W is positive. When heat is released or given off, Q is negative. When work is done by a system, the masseuse is going to be pooped. So he, even though he's getting a tip, W will be less than 0, so negative. All right? But when think about yourself as the system, when you go get a massage and work is done on you, positive. Don't think you'll see much of that. In regard to the change in enthalpy, remember enthalpy cannot be measured directly, so we measure the change in. It's negative in exothermic. Be careful here. Temperature is going to increase. We've talked about that. When you dilute acid in water, it is highly exothermic. You would never have acid and pour water on it because it's so exothermic it could explode. So whenever you dilute acid, you always have a bed of water. You put the acid in. Then you can add some more water, but you want that water bed there so it absorbs some of the heat that's released before it's all just going out and potentially exploding. Decomp requires energy to break things up, endothermic. Synthesis, typically exo, not always, but usually. Combustion reactions are exothermic. This is why you don't smoke at the gas station. Very, very dangerous. Reactions in which bonds are made, exothermic. I'll teach a trick with that at the end. Reactions in which bonds are broken, and thinking about it, breaking up is hard to do. Endothermic, it requires a lot of energy. Freezing and condensation, exo, melting and boiling, endo. And when dissolving, typically you're going to get an increase in entropy unless they tell you otherwise, and that would be due to hydration shells. You always want to keep some very simple concepts in mind. This is something you would all have seen in honors. Let's take a look here. So we know this is melting, we know this is boiling, traveling in this direction. We know delta H is positive, melting is endothermic, vaporizing or boiling, endothermic. Delta S here would be positive as well. Solids are ordered, gases are disordered. In the reverse direction, then, we know that delta H is negative, exothermic. Delta S would be negative as well. Remember, negative delta S, no, 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 negative order, negative order, negative order. Order is determined by delta S, not by delta H. Sound familiar? And when you consider dissolving, for example, if you had magnesium sulfate, solid, dissolve it in water, and you're going to get magnesium ion and sulfate ion, both of which is aqueous. You will see the increase in entropy because aqueous species far more disordered than solids, although you can get hydration shells. When you want to alter delta H, remember this is an extensive property, so very different from your E cells. If you reverse the process, you change the sign. If more than 1 mole or less than 1 mole is utilized, you'll multiply the delta H by that factor. When you're calculating delta H, remember it is products minus reactants. You want to go PP before you start running. Products minus reactants. Standard conditions, not STP, 1 atmosphere and 25 degrees Celsius. Any free element, diatomic element, polyatomic elements is 0. There should be a 2 right here. I'm not sure where it went, but bromine, of course, is diatomic. The other thing I want to mention to you, and we talked about this the other day, you can calculate delta H of a reaction doing delta H's of formations of products minus reactants, but you also can do it for bond energy, and this is the one time it's going to be reactants minus products, and we talked about little burps or whatever it is you need to remember that. You've seen Hess's law before. You saw it in honors. It's one of the few things I do in honors that's a way above, but it gives you a great jump start for AP. Hess's law, where if you can sum the equations together, you can sum their delta H's. Shown here is a heating curve. Remember, solid, liquid, gas. Here are the solid-liquid transitions and the liquid-gas transition. This curve is not drawn to scale. Ideally, this line here should be drawn much, much longer than this one. Remember, it takes far more heat to undergo vaporization because you must break all the IMFs, maybe not just some as you would with melting. Here's your delta H of vape. Delta H of fusion shown here. Remember, with entropy and delta G, you can do all of them as products minus reactants because you have a state function. And the other thing I want to remind you of, and we'll take a look, most of these equations are provided to you. You'll remember from both honors and AP that delta G is equal to delta H minus T delta S, and I wrote on there, make sure the units are same. This is going to be in kilojoules or kilojoules per mole. When you do this, you better get Kelvin here, and you better get this in kilojoules per mole Kelvin. The delta S most likely is going to be in joules per mole Kelvin. You will divide by 1,000 or move the decimal 3 to the left. To go from degrees Celsius to Kelvin, you add 273. Keep it simple. Couple other things here. Second and third laws. Third law says the entropy of a pure, perfect crystal is 0 at 0 Kelvin. That's because there's no atomic or molecular motion at 0 Kelvin. Second law of Thermo says that spontaneous or thermodynamically favorable processes will increase the entropy of the universe. You may want to have thermodynamically favorable. I don't know. I modified this off somebody's. It's very hard to make changes. So the change in entropy for the universe is going to be greater than 0. In regard to entropy changes, we had indicated that on our diagram. Positive entropy, disorder, negative entropy, order. You'll see an increase in entropy when solids melt, or you get vaporization, dissolving of solids in solvents. Also, when you get an increase in the number of moles of gases, for example, let's say that you were going to decompose dinitrogen pentoxide, you would get nitrogen dioxide and oxygen gas. And what you're seeing in this instance is delta S here would be positive because you have 5 moles of gaseous product compared to 2 moles of gaseous reactant. when you increase the number of moles of gas going from reactant to product, that is disorder, a positive entropy. Yes, yes? All right, so it all looks familiar. Keep in mind here as we manipulate this, let me give you a good review of this. This always causes a slight problem. With delta G, and actually I just did this in honors and I went over it for like 10 minutes just banging it hard, and there's just a very, very little video if you feel like you don't have it after today. Keep in mind that an exothermic reaction that illustrates disorder, a negative minus a positive, will always give rise to a thermodynamically favorable reaction.
Can you go over like what drives an equation?
That's right here, right here. I'm going to hit it right here. You've got it. An endothermic reaction that favors order will never give rise to a thermodynamically favorable reaction. And now in regard to driving, let's say we have an exothermic reaction that illustrates order. A negative minus a negative, you're not sure. For a thermodynamically favorable reaction, what would drive it? The enthalpy or the entropy? It's got to be this. You want the temperature to be very low here, and the enthalpy term will predominate and drive the thermodynamically favorable reaction. In contrast, if you have an endothermic reaction that illustrates disorder and you give rise to a thermodynamically favorable reaction, you've got a positive minus a positive. You want this to be negative. So which term has to be larger, the delta H or the T delta S?
T delta S.
So that means that the entropy is going to drive it at large temperature. This term won't be as relevant, and the entropy will drive it here.
But at a low temperature, you'd say enthalpy would drive it, right?
That's correct. But I'm trying to indicate in this, and then you wouldn't get thermodynamic favorability. So I'm trying to indicate what drives it for thermodynamic favorability where delta G is negative.
When would it be both?
Right?
When would both drive it?
Oh, the only way you could get both to drive it would be that, right?
Or the one below it, right?
Drive it in a non-favorable manner. But if you're going to drive, you want to get somewhere. So you want thermodynamic favorability, I would think. The other thing you do want to make sure that you know is
So
when...
you'd have to have an exothermic at high temperature, right? That's what the question would have to say in order for it to be both. To drive it, you'd have to have
An exothermic disordered,
with high temperature.
yeah. Well, at any temperature. At any temperature. At any temperature, if you've got exothermic disorder, they both drive it.
Okay.
Delta G, KEQ. Delta G is 0, KEQ is 1, so you're at equilibrium. When delta G is negative, KEQ will be greater than 1. The forward reaction is favored. Delta G is positive, KEQ is less than 1. Reverse reaction is favored. And then I think some of the kids missed this last question, where if you have delta G and you want to get KEQ, this formula is not given directly on your formula sheet. KEQ is E negative delta G RT.
You can get it derivatively.
Yeah, you can. this has to be in joules. And this R has to be the 8.314
And T has
joules
to be-
over mole Kelvin, and T must be in Kelvin. Really, the only time you leave temperature in degrees Celsius is when you have a change in temperature, and that's because the change is the same regardless. All right, so those are your thermo terms. And then we hit that box already here, so that's giving you all the variations. And that's your thermo. Now, the question I was looking at was this one. And this is something you would have access to. This is a lab-based challenging question. Here's your reaction. Student was assigned the task of determining the enthalpy change for the reaction between solid magnesium oxide and aqueous HCl represented by the net ionic equation above. The student uses a polystyrene cup calorimeter and performs 4 trials. Data for each trial are shown. I do want to ask one question. Looking at that reaction, as the reaction proceeds, what happens to the pH? It increases because you're using the proton. Okay, now it says, which is the limiting reactant in all 4 trials? Hydrochloric acid or magnesium oxide? And it should be crystal clear that this is the hydrochloric acid. How come I only wrote proton?
Isn't that ionic?
HCl is a strong acid that ionizes completely. So, how are you going to figure out limiting reactant? For HCl, what do they give you?
Volume,
The volume and the
molarity.
concentration. So 1 times 0.1 is 0.10 moles. Now how are you going to get it for magnesium oxide?
Molar mass.
What's molar mass going to do? What are you trying to get to?
Moles.
Moles. Okay? So what do you got?
Would you divide the 0.1 by 2?
You can try either one and see. We've got this.
You only have to do it for 1 trial, right? Because it says it's the same for all 4.
Well, you do have different masses, so go with I think I'd go with the bigger number and see if it made a difference. So you know, in regard to this one, you've got 1 molar times 0.1. Oh yeah, you know that bothered me when I saw it. It's written backward, and I did it backward. Do you see how they did that? The equation is written differently than the table, and I noticed it initially. I was going to say something. I'm like, oh, they won't be confused, and you weren't. Eventually, it'll come out, right?
How do you know that it's acidified? How's the game
Not
worse
great
today?
science, Mahi.
Okay, how's the game worse today?
Getting less acidic.
Oh, last night's
So that's 0.1
Okay, that makes sense. I knew H was
moles. And on this one, you have 0.50 grams.
Wait a minute.
I feel like because you taught me how to change it, but then it's like stuck in that, and I don't want it.
So you go back to flow.
I'm not.
Second side.
All right, so proton needs to be 2 times as much as the magnesium oxide, right? Is it? Well over that, even if you use the larger.
So then magnesium is the.
Or if you don't see that, if you divide this by 2, you'd have 0.05. It would still be greater here. So clearly what you're looking at, and this is where some of you are just doing that and coming up with an answer. Be careful here. What you want to indicate is that magnesium hydroxide is the limiting reagent, because, how do you want to state this?
0.012 moles is stoichiometrically less than ion 5.
How would you show it? Based on the 1 to 2 mole ratio? You can write that, that's fine. Is the limiting reagent because less magnesium hydroxide is provided stoichiometrically based on the 1 to 2 mole ratio. Or what I think what you guys probably are going to do is divide this by 2 and show that, and that's fine too. Alrighty. The data in one of the trials is inconsistent with the data in the other 3. Identify the trial with inconsistent data and draw a line through the data from that trial in the table above. Explain how you identified the inconsistent data.
What does this have to do with 30?
Initial and final temps. Time's a little short. You may want to scribble down 2013, so if you want to yank it up, you can.
Why were the kids last year so upset that they were?
What do you got here? What do you think you're crossing out? Is there one that just looks very different? You want to cross out one?
Yeah.
How come?
Only increases by 1 degree.
Only increases by 1 degree. So it looks grossly different than number 3, right? So here you have an increase of 2.1 for that amount. And here you have an increase of 4.1 and 4.0 for that amount. So it does appear to look different, yes? Mm-hmm.
No, how do you know it's not 3 that's wrong?
No, but listen to what she said.
Because that one, so they're using 20.25 grams instead of 0.5, so it's half as many grams. And the 50.5 grams increased by 4 degrees, and that one increases by 2.
Yep.
So like half.
That looks good. And let's see what they said here. And we were correct here. They say by the stoichiometry, and so they did it very similarly. Trial 1 is inconsistent, and they're saying the temperature change should be directly proportional to the amount of limiting reactant present. And so she saw that relationship and went with it. So then, in that case, yes. And I would stay with that type of question to review a few key things. With thermo, make sure you understand the entropy, the delta G, thermodynamic favorability. I think you'll be very strong there. Also think about how thermo links to other topics such as electrochemistry. You can get a kinetics linkage. You've seen thermo on pieces of everything.